Hey everybody. So over the years I've read a lot about extinct human ancestors and I've always wanted to know what they look like. So here's an idea about how to use AI to recreate the lost faces of human evolution. So what did our extinct prehistoric ancestors look like? For more than a century, artists have tried to rebuild ancient human faces from skulls. They were forced to use their imagination and ingenuity to do it. Until recently, that meant the faces of Neanderthals, Australopithecines, Homo floresiensis, and earlier hominins were partly unanswerable questions. Modern AI changes the terms of that question. So the idea here is pretty simple. We can show an AI model thousands of paired examples where the input is a 3D skull and the output is the real face that belonged to it. We start with humans, where matched medical scans exist, then add living apes and monkeys to teach the system how primate skull shape influences the soft tissue above it. Once the model learns those relationships, we can point it at fossil skulls and ask, given this bone structure, what faces are most consistent with what you've learned? So let's take a look here. This is the diagram that I made to kind of represent this. So this is machine learning method for predicting human ancestor facial features from skulls. So first, you train a neural network on skulls and matched human faces to teach it how skull shape influences facial features. Basically, you're turning the skull into a number and you're turning a picture of the face or a model of the head into a number. And you're forcing these two different neural networks that may be pre-trained, a skull encoder, which could be a 3D transformer, and a face generator, such as a diffusion model. You're linking them together and you're forcing this system to learn how to predict one number from the other number by giving it real data, right? So first you show it human skulls and it learns how skulls map onto human facial features by looking at real pictures of real people. And scans of their skulls or measurements of their skulls, pictures of their skulls. There's a number of ways you could do it. Two is expose the model to data from living apes and monkeys to teach it to predict facial features from all primate skulls. So it's going to be looking at everything from capuchins to gorillas. And this will be the same neural networks that looked at the people. Right? And then number three is use the model to infer facial characteristics of extinct human ancestors and other hominins from fossil skulls. So we don't have faces for these guys. We don't have soft tissues from them, right? But we do have their bones, including their skulls. And I think that we could just insert their skulls into a system like this and probably get a really good approximation of what they would have looked like. Way better than any artist could imagine. So to back up for just a second, even though cartilage and soft tissues don't fossilize, the skull gives strong hints. Its bony architecture sharply constrains the overall head shape, including forehead slope, brow, zygomatic arches, dental arcade, mandible, nasal aperture, chin, and muscle attachment sites. So if we can feed enough of these skull face pairs to a machine learning model, it will start to learn the regularities and turn them into a mathematical function. It will learn, for example, how the curve of the zygomatic arch relates to cheek contour, how the nasal aperture and spine relate to the bridge of the nose, and how jaw robustness relates to mouth shape. Widening the training set with non-human primates will keep the model from overfitting to modern humans. The apes and monkeys will also extend the range of skull shapes and soft tissues and provide a phylogenetic bridge so that all the model must do is create interpolations. This project should use interpolations, these hominins came basically between humans and apes. So it's not an extrapolation, it's an interpolation, and that's much easier to do. So this project should use a large, highly diverse sample of humans, as well as several members from all of the great apes, chimps, bonobos, gorillas, orangutans, lesser apes, gibbons, and possibly also monkeys as well. I think definitely monkeys now. It might help to remove and maybe even other mammals, could make it a better predictor. We won't know until we try. It might help to remove the hair from at least some of the primate 3D models so that the features that are normally covered by fur can be mapped. So here's the GitHub page that I started for this project, and it includes a toy demo of how this would work. So here's the page, and here is some of the code. And I think that this is going to be more and more possible as agentic programming becomes more and more widespread and more competent. So this system would effectively be teaching the AI how to translate between skulls and faces. And remember, translation is what the transformer AI architecture was originally developed to accomplish. And GPT is a transformer, right? So the AI would learn a skull-to-face vocabulary from living species and then use it to translate fossil skulls. It's like a police sketch process, except now the skull is the witness. So, and I think interestingly, this could be used with any extinct animals that we have skeletons for with existing relatives. And so it could work for dinosaurs and much else that you could imagine. So how would this work for dinosaurs? Same way. You train the model on skulls and matched faces of living animals to teach it how skull shape influences facial features. Then you use the model to infer and generate imagery of facial characteristics of extinct animals from their fossil skulls. So you would include pictures and skulls from many, many turtles, alligators, crocodiles, snakes, lizards, birds, as much as you could. And then you probably would include fish and amphibians. And the system would probably give a lot better guesses than Hollywood CGI artists are able to kind of conjure up. So there are many human artists who have created paleo art depictions of prehistoric human ancestors. Some of these paintings are exquisite and highly evocative. The human artists make their design decisions using the extremely sophisticated neural networks in their heads, right, their brain. But the job would be better accomplished by machines due to their computational advantages. Making a precise statistical prediction about a face from a reference skull involves attention to more features and patterns than humans are capable of keeping in mind at once. There are all kinds of hidden, latent correlations that the human mind does not notice, but that machine learning will pick up on very easily. And this is why we should use AI for a project like this. So I'd like to point out that I have a similar machine learning pipeline that could help us make more informed guesses about the genomes and brains of extinct animals. So just to show you really quick, this is another similar pipeline that would make predictions about genomes. So you turn the genome and the full body skeleton into a number, and you teach it how to go back and forth with existing animals. And then we don't have anything from dinosaurs but the skeleton. But by using this pipeline, we've created like a lock and key mechanism where the dinosaur skeleton is the key for unlocking ideas about their genome. So this is a whole nother thing. And then this is another concept here, reconstructing brains from endocasts. So we don't have any brains. They're soft tissue. They don't fossilize well, if at all. But we could create a similar machine learning pipeline to make guesses about what their brains would have been like from the endocasts of existing animals. So if you're interested in a hominid brain, you would take the endocasts, which is the inside of the skull of apes and humans, and you compare that to their physical brains. And then you train the system to do that, and then you give it the endocasts of hominins, like a Neanderthal or Homo floresiensis or something like that. Okay, so how would this system, so now we're getting back to faces and bodies and appearance, right? Outside of brain, outside of genome, back to appearance. So how would this system work? At its core, the machine learning system has two halves. The first part of this AI system is a transformer, which is a type of neural network that pays attention to the geometric relationships in the 3D skull, how different parts of the bone relate to each other, and how they shape the face. It would work as a geometric encoder that studies the skull as a true 3D object rather than a photograph. We would feed it cleaned skull meshes or dense point clouds in a standard pose. This 3D transformer would learn which bony regions covary, distilling the skull into a compact numerical description. And just to go ahead and mention, you could do this for skulls, but you could also do this for bodies and include the entire skeleton. So just keep that in mind moving forward. So this first system would then lead to an image generation system that would create a prediction of the face it expects to lie on top of each skull. So again, the first system is the 3D model of the bone, and then the second system is an image generation system, kind of like the ones we use when we use AI to create images from prompts. So thus, during training, it would try to generate, using an imagery generation technique called diffusion, a face for each skull, and it would get feedback based on the actual ground truth face. Over time, it would learn the mapping of skulls to face and get really good at understanding which skull features correspond to which facial features. The best fit here for the face generator may be a conditional diffusion model that would take the transformer's latent description of the skull and sample many faces conditioned on it. Most state-of-the-art image generators today are from the diffusion family. They dominate because they're able to train, scale well, condition cleanly on text or other inputs, and naturally produce diverse samples rather than collapsing to a single look. Adobe Firefly, Midjourney, DALL-E 3, Stable Diffusion, Google's Image Inline, Runway's recent models, and many research systems are all, such similar research systems are all diffusion flow variants under the hood. For a single, simple stack, a diffusion network over a mesh point representation with the skull encoder's tokens plugged in via cross-attention is probably the clean, modern choice. So hundreds of pairs might get this model off the ground, but it would need thousands of human and primate pairs to show some precision. Of course, we wouldn't want to reinvent the wheel, so we wouldn't start entirely from scratch. Instead, we use something known as transfer learning, where we start with an existing model that's already been trained on a large amount of 3D shape or image data. These models have a good baseline understanding of physical general patterns, even those related to faces. Then we would fine-tune it with the skull-face pairs so it learns the specialized task of transforming skulls to faces. By leveraging an existing image generator or 3D model and then adapting it, we could save a lot of time and data. So those neural networks you saw earlier in the black and white diagram at the top, I'm saying that we could be using So once that mapping is learned, we can turn it toward the past. So once it's trained on existing animals, we can present a well-preserved Neanderthal cranium or the small skull of Homo floresiensis and ask the model to propose faces that are consistent with the bone. Some of the skulls coming from paleoanthropology departments are crushed. However, we already have algorithms that can digitally uncollapse a fossil that was crushed in the ground so that the AI model sees a truer shape before it begins to infer a face. The right output is not a single portrait. Bone to face is an underdetermined problem, and many faces can fit the same skull. A responsible system would produce an ensemble of possibilities that agree where the skull is informative and vary where it's silent. The bony frame nails down head shape, brow, jawline, and overall proportions. The details that live in cartilage and fat, such as the tip of the nose, the lips, and the ears, carry wider uncertainty. A good system would make that uncertainty visible and apparent to users. So as you can see, this picture right here on the right of a hominid face or a monkey face or whatever it is a machine learning picture, and it probably looks pretty accurate. Now that's going to be heavily influenced by artists' conceptions of how these animals would look, and influenced by all kind of other things that we can't control, right? So this was created by a general image generator, but ours would be much more specific, conditioned mostly on real data. So next, we'd want to show that transforming skulls to faces works on humans with measurable accuracy and well-calibrated uncertainty. Then we'd want to show that this generalizes to other primates by holding out a species, such as orangutans, from training, but then testing the model's ability to recreate that species' face after training. Only then would we present fossils. With a team of researchers or with a sufficiently advanced AI agent, the fossil could be presented alongside expert commentary and comparisons to traditional hand-built reconstructions. So again, these were all created by an artist, but I'd like to see what a machine learning system would do. And as you can imagine, these machine learning systems keep getting better and better. So I think over time they would become more and more accurate. So what would this system give us? Several extra sources of information can be used to help reduce guesswork. Forensic science has measured average soft tissue thickness at standard points on the face across age, sex, and ancestry. Those tables can be used as anchors. Ancient DNA, where we have it, could inform pigmentation and other features. Known information pertaining to the genes that influence skin, hair, and eye color can narrow the palette for Neanderthals and some early modern humans. Comparative anatomy helps too. A specimen placed on a particular branch of the family tree should look like its neighbors on that branch. A reconstruction of Australopithecus should not drift toward a modern human nose, and a reconstruction of early Homo should not drift toward a chimp. A museum could present the results in a way that reveals both the power and the limits of the method. Imagine standing in front of a fossil cranium and a rotating 3D viewer. You can toggle through 20 plausible faces derived from the same skull. A simple overlay highlights the regions where the model is most confident in green and least confident in red. A control lets you alter the features based on ancient DNA when it exists. It invites the public to see how bone constrains flesh and where knowledge gives way to uncertainty. Reconstruction should be clearly labeled as probabilistic, and training data should be de-identified, to maintain privacy and anonymity. What might we actually see if we were to build this model? Neanderthals provide a best case because we have several complete crania and high-quality DNA. The ensemble would likely be tight where bones speak strongly and more variable around the nose and lips. The tiny LB1 skull from Flores would show a different pattern, with robust jaws and a short midface, but wider uncertainty in soft tissue. A classic Australopithecus like Ms. Plez would land in between ape-like prognathism and human-like flattening. Denisovans are the opposite case. For Denisova hominins, we have remarkable DNA and finger fossils, but no fossil skulls, so this technique could not be applied to them, at least not yet. Okay, so for the conclusion. I remember back in my 20s, I thought the face of an extinct hominin was one of the greatest mysteries of science and something I very much longed to see. Although these faces will never be known with finality, with careful methods, we can recover their outlines and likely expressions. We can give museums new tools to teach. We can give readers a stronger sense of kinship. The result is not just a new picture in a textbook, it's a new way to talk with the public about evidence. A single confident portrait invites argument about smiles and haircuts. An interactive ensemble would invite questions about how bone shapes flesh, about what DNA can and cannot tell us, and about how evolution channels variation. It lets us look at ancestors in the eyes, while remembering that some parts of that gaze come from rock and measurement, and some parts come from honest uncertainty. I've always thought it unfortunate that most modern depictions make hominins look brutish. I think the main takeaway from the high-fidelity facial recreations is that we will see these people were beautiful and noble. Some of them would have been diminutive and adorable. Others would have been intimidating due to their size and robusticity. Some of the phylogenetically older ones might be eerie looking, but their visages would help us see our continuity with the rest of the primate order. I predict here that we'll see the intellect in their eyes, we'll find them attractive, and we'll see them as cousins and equals. I believe that they will invariably look interesting, making us want to reach out, talk, and engage with them. But I think in the not-so-distant future, AI could help us have a scientifically accurate, communicative interaction with the avatar of a Homo erectus individual. That might sound kind of crazy, but I guess it could be fun. Before we wrap up here, let's take a look at which hominin species we actually have skulls from. So these are the bones or the skulls that we'd be able to enter into this neural network. to make predictions about. So here's a list of hominin taxa with substantially complete crania and skulls, good enough for 3D modeling, that this pipeline could take as inputs. They're grouped here roughly by era with exemplar specimens in brackets. So by era goes oldest to newest, and you see that we go through Australopithecines, through Paranthropus, down through different Homo species, such as ergaster and erectus. There are quite a few really good ones that are complete. And the idea, you guys, is that, okay, so yeah, we don't have Denisovan. There's a few of these that we just don't have. But the idea is we could take those skulls, which are in museums, turn them into numbers, and then plug them in right here to see what they would have looked like when alive.